Okay, welcome back, everybody. So, last time we did a pretty neat application of the pigeonhole principle. I think this was originally from an argument due to Erdos and Scares. Yeah, I think that's it. So this is from a paper of Erdos and Scares. Uh, but this is an example where you saw how once the problem was set up, there was a lot of setup involved here, but really it was one single application of the pigeonhole principle here. And you might complain and say, well, the problem statement was kind of set up in a way specifically to use the pigeonhole principle. That's true, but sometimes finding out the right question to ask is a huge part of the struggle. Um, so that's fine. There's nothing wrong with that. One more application I want to talk about, though, in an area that might seemingly, not have too much intuition for how the pigeonhole principle would be used in such a way. So one more pigeonhole application. I'm not going to do this full proof. I will tell you where you can read about it, but I wanted to present it at least because I think it's very interesting use of this. And so this is approximating irrationals by rationals. You hear something like that and you're like, oh God, this is this is a real analysis thing. This is a math 410 type thing going on here. What am I doing with my discrete math concerns in this area, right? Well, to see what it is we're talking about here, so let alpha be irrational, i.e. alpha is a real number that is not in the rational. So we could write it like this. It's a real number that's not in the rationals. There we go. Okay. So it cannot be expressed as a ratio of two integers. Of course, you might say, well, if we look at like a continuum, if I look at an interval, right, say of integers, or sorry, of real numbers a and b, with a strictly less than b, you know how this interval notation works. This has infinitely many rational numbers. So you might say, all right, if alpha then is in this interval, then you might say, okay, well, there's infinitely many rational numbers, and surely there exist rational numbers arbitrarily close to alpha. This is really a question about the density of these sets. So you might recall from Math 410, if you've taken Math 410, you might recall from Math 410 questions about density of sets in other sets and exactly what that means. So this is statements about density of either the rationals or irrationals here in this interval. Might be flooding back into your mind now. But let's, instead of just talking about any rationals that might approximate this, right? So there are infinitely many rationals close to alpha in the interval AB. Okay, maybe you think of it like that. But let's restrict the rationals that we're talking about to a set of fractions with bounded denominator. So how close can we get to alpha now? So here's a question. Given an irrational number, alpha, okay, and a positive integer, say q, does there exist a rational number? Well, Now, if it is a rational number, we can write it as a p over q, or p and q are integers, with q between 1 and big Q, and the distance between alpha and p over q is especially small. And a follow-up question, how small can we guarantee? Okay. Now, you can start to think about partitioning intervals. You say alpha has to lie in some interval like k over q and between k over q and k plus 1 over q, so you can think about incrementing the numerators. Here, alpha's got to lie in one of those, and you can think about subdividing those and seeing like how close you could get. Using again the fact that the rationals are dense, so you can find plenty of them. Okay, right, in an interval. So this is kind of the maybe your intuition, but actually we could show something stronger than that using the pigeonhole principle. So some notation first. This is notation that you are likely to already be familiar with. So the floor function for a real number x. This is the floor, or the integer part of x. This is, of course, the largest integer m satisfying m is less than or equal to x. So this is largest integer m such that m is less than or equal to x. The ceiling function of x. This is the smallest integer m satisfying x is less than or equal to m. So this is smallest integer m such that x is less than or equal to m. Okay. Notice one more thing. I'm going to use squiggle brackets here around x to denote what I call the fractional part of x. This is going to be x minus the floor function applied to x. So, quick example. If x is pi, right, then what is the floor function of pi? Well, it's 3. What is the ceiling function of pi? It's 4. What is the fractional part of pi? This would be its decimal expansion. We take its decimal expansion, we subtract 3 from it, so I get 0.1415926535897932384, and so on. I think that's right. I know more digits of E Okay, then pi. I think that's as good as I can do for pi right now. So these are things that you've seen before, but we need these expressions. And so, why do I need these? I need these to parse through the proof of this thing, which again I'm going to leave to you all. But the answer to this question of can we make this small and how small can we guarantee, this is fully answered in the following theorem. This is due to Dirichlet. So this is Dirichlet's approximation theorem. Okay, so suppose alpha is an irrational real number. And q is a positive integer. Then there exists a rational number p over q with little q between 1 and big Q satisfying that the distance between our irrational alpha and this rational p and q is less than 1 over q times big Q plus 1. This theorem on its face, it doesn't appear clear where the pigeonhole principle is going to be used. If you want to see how this is going to be used, so idea. The full proof you can find on pages 153 and 154. Because looking at this, you're asking yourself, I can hear you now, you're asking yourself, how does the pigeonhole principle factor in here at all, right? This doesn't sound like something where the pigeonhole principle could be used. But the idea, divide the interval 0 to 1 into big Q plus 1 subintervals of equal length. So subintervals are 0 to 1 over big Q plus 1. And then, I should include left endpoint. So this is 1 over big Q plus 1 to 2 over big Q plus 1. And so on in this fashion, such that here I have Q minus 1 over Q plus 1 to Q over Q plus 1. And then the last one is Q over Q plus 1 to 1. Okay, so you can check there's Q plus 1 of those. They have the same length. And then we have Q plus 2 real numbers. And then each of the big Q plus 2 real numbers, let's say what they are. So 0, the fractional part of alpha, the fractional part of 2 alpha, so on, fractional part of Q alpha, and 1 lies in the subinterval 0 to 1 by pigeonhole principle. There's q plus 2 of these. They lie somewhere in 0 to 1. 0 to 1 can be divided into q plus 1 subintervals. So by pigeonhole principle, at least 2 of them must lie in the same subinterval. That is where the pigeonhole principle is used. The rest of the proof continues from there. This is the most important step in the proof. Everything else is basically unpacking what this means and getting the statement from that. So this is the key step in the proof. After this, it's like I said, just kind of unpacking what all this means. So I just wanted to include this to show a potential example of applying the pigeonhole principle in a setting that it might not immediately be clear like how it could apply. And this is, this is one of the beautiful things about combinatorics is that it can show up in settings, of course, where like on its face it doesn't look like what you're doing would be amenable to this sort of discrete or finite math stuff, but it is. So here is a decent example of that, and this is essentially a consequence of the pigeonhole principle, which is one of the, it's one of the foundational tools we have. Okay, so now moving on from the pigeonhole principle. There is another principle that, again, you have likely encountered if you've taken almost any probability class. Certainly if you've taken like Stat 410, this is done near the very beginning. Depending on the instructor, it might not be done in complete generality, but here's the principle itself. So the principle of inclusion and exclusion. So it is best, I think, to illustrate this with a big example. State the theorem that gives the general form of it, and then do a few applications. Because like the pigeonhole principle, inclusion-exclusion seems to have a very narrow focus, but you don't have a full appreciation for how it can be applied until you see a few of those examples. So in this instance, what are the examples? Let's say that I have 50 beads in some drawer. Okay, so 50 beads. We'll say 25 are glass, 30 are red, 20 are spherical, 18 are red glass, 12 are glass spheres, 15 are red spheres, 8 are red glass spheres. Question: how many beads are neither red nor glass nor spheres? So the idea is to use a Venn diagram. Of course, again, you're familiar with actual Venn diagrams, right? Imagine being someone that's not used to actually using, actual precise Venn diagrams, right? Maybe you're using kind of Venn diagrams in some kind of literature class or something, right? And you'd be in very, very squishy with what with what these things mean. But no, we are using actual Venn diagrams here. So I want to try to organize this with some overlapping sets here. So the sets I'll use are, we'll say G are the glass beads, and R are the red beads, and S are the spherical beads. So that in this way, I'm looking for beads that are neither in G, R, or S, right? So in none of those. And so if I draw a Venn diagram, maybe I'll give myself more room here so that it's more visible what's going on. So let's actually draw these regions here. So here's G, we'll say. This is G, and then this is R. Then this is S. And let's use my info to fill these in. So here. So we got 50 beads total. So if you like, I have like an exterior. I'll box it off here. I have like an exterior. And when I ask the question, how many beads are neither red nor glass nor spheres, I'm looking for a bead here, right? I'm looking for a bead that is outside all of these. But let's actually label how many I have here, right? So the thing is that I have 25 glass beads. So all total, all of the glass beads there's 25 of them. So let's see here. I know I have 30 red, 20 spherical. So I know the total counts on each of these. Of course, I know the total counts of beads. But let's try to enumerate how many of these I have in each region, right? So for instance, here, this region indicates beads that are glass, red, and spherical. And I'm told that I have 8 such beads. So I know that there's 8 of those. I have 12 glass spheres. Glass spheres, though, are like everything here, right? It's not just what's here. It's not just what's here. Something here would also be a glass sphere. It would just be a red glass sphere. So glass spheres are everything here. If there's 8 things here, then that means there have to be 4 objects here that are glass spheres that are not red, right? Okay. I know that I have 15 total red spheres, right? So 15 total red spheres. So if here is 8, the other red spheres are what is here. So there's got to be 7 of those. Okay. Well, what about red glass? There's 18 of those. Here's 8. So then there have to be 10 here. Okay. Now that I've figured out these intersections working out here, I know that the number of spherical beads, there's 20 of them. So here's 7, here's 8, so 15 plus 4 is 19. So there is only a single spherical bead that is not glass nor red, right? Similarly, there are 30 red spheres, but here's 10, here's 8, here's 7, so that's 10 plus 15, 25, so there's only 5 beads that are red but not glass nor spherical. And then lastly, there's 25 total glass beads, 10 plus 8 plus 4, that's 22. There's only 25 of them, so only 3 are glass but not red or spherical. Okay. Now, I can, of course, now I have all of the info needed to just directly figure out what this answer is, right? But what is actually more convenient, or maybe, especially if I'm trying to do this in a way that is easily generalizable, right? That generalizes what I'm trying to do in a nice way so that I can see how I would move beyond my original idea. The idea is count the set G union R union S, i.e., find the cardinality of G union R union S. What is the immediate problem with this? So, immediate problem. Do this without double counting. Or triple counting, even. What do I mean by that? I mean, if I'm looking at this picture and I'm trying to count everything, first of all, why does counting this set, why does finding this help us? Because then our answer is total, so the total number of beads minus everything in this set. Why? Because something in this set is either glass or red or spherical. But we were exactly asking how many beads are neither red nor glass nor spherical. So we're asking for something that is not here. Well, how many things are not here? That's the total number of beads, 50, minus the number of beads that are either glass, red, or spherical. Right? We don't want it to be any of those. So we want to count this and then subtract it from the total number of beads. But how to do this without multi-counting? Because the problem is that there's these overlaps. This would get counted twice. If we were just naively counting, this would get counted when you count the elements here, and then it would get counted again. These 10 would get counted again when you count the elements in the red beads. This would get triple counted because this has overlap with G, R, and S. So these 8 would get counted when you count the elements in G. They would get counted again when you count the elements of R. They would get counted again when you count the elements of S. So this region would be triple counted. These two regions, or these 3 regions, would be double counted if we were being as naive as possible, right? And just going set by set. So we're adding all the elements of G, then we add the elements of R, then we add the elements of S. That's not the way to do it, right? That is not going to give us this answer because we're double and triple counting here. So then how do we do this? In order to ensure that we are not multi-counting, when we do this, So we are counting the things in this union of these three sets. So how about we do the completely naive thing and just sum the total number of glass, red, and spherical beads. So total number of glass plus total number of red plus total number of spherical beads. Now, to account for the double counting, what we would then do is we would subtract off some of these regions that had been double counted. So let's focus on the regions taken two at a time. So let's subtract off from this the intersection of G and S. Then let's subtract off the intersection of G and R. Then let's subtract off the intersection of R and S. Let's see if this has fully accounted for the multi-counting. So G plus R plus S, that gives me all of G, all of R, all of S. So if we're keeping track here, these regions have been double counted and this region has been triple counted. Okay? So when I subtract off G intersect S, I'm subtracting off this region. So now this region had been double counted, now it is single counted. This region had been triple counted, now it is double counted. Okay. So this region's good, this region's good, this region's good. Now this region is good. I'm subtracting off G intersect R here. That subtracts off this region. This region was previously, this region with the 10 was previously double counted. Getting subtracted off, now it is single counted. We're happy. This was originally triple counted. We subtracted off G intersect S, so now it was just double counted. We have subtracted it off again, so now it is actually single counted. So this is good now. And we're happy. Then we have this region that's not good. So we subtract off R intersect S. So we're subtracting off this entire region. What that does is now this region of 7 beads was double counted. Now it is single counted. But we also took off another copy of this overlap, which previously was fine at the last step. So now we have taken off one too many of these. We are now undercounting this region by not counting it at all. So we need to add it back in. And we add it back in the last term, which is G intersect R intersect S. We add it back in to single count it again, and now we single count all regions, and this does it. This is called the inclusion-exclusion principle. And I'm going to explain to you how this can easily be generalized here as this alternating sum. So I'm going to read out in words how this is, then we're actually going to solve our problem. So reading out in words these things. This is so to count the union of three sets G, R, and S, to count the elements of this, I first count the elements in each of the sets taken one at a time. So all of G, all of R, all of S. I subtract from that intersections of sets taken two at a time. So minus the intersection of G intersect S, minus the intersection of G intersect R, minus the intersection of R and S. Okay. And then I add to that the intersections of these sets taken 3 at a time. Then you see how this would go for 4 sets, 5 sets, 6 sets. For 4 sets, I would do the sum of each of the sets taken 1 at a time, so there would be 4 of those. Then I would subtract from that the sets taken 2 at a time, the intersection of sets taken 2 at a time, right? Then I would add to that the intersections taken 3 at a time. Then I would subtract from that the intersections taken 4 at a time. That's how the pattern goes here, okay? The answer to our question, you can check this yourself, is 12. There are 12 such beads, so use this to check that now we are able to say that the number of beads outside here has to be 12. You could likely just do this quickly adding up here. You can use this inclusion-exclusion principle to get it immediately because you just, it's total number of beads minus that. It's going to be 50 minus 38 here, and it's going to give you 12. So this pattern here is the most important one to notice, the case for 3 sets. Once you see it for 4 sets and how it goes, you can immediately see the pattern. I'm going to write that out now, but before I do, let's do some notation here. So suppose we have a collection of n distinct objects. Okay, so we have n distinct objects here. And let's say each object may satisfy one or more properties that we're going to label. And each object satisfies one or more properties that we label A1, A2, out to some A sub R. Okay. Define n of A sub 1, or I'll just go ahead and just define it for A sub I. So n of A sub I is defined to be the number of objects having property A sub I. Let n of A sub I, A sub j be the number having both a property A sub I and A sub j. So the number of objects having both property A sub I and A sub j. And similar for any of these. So let's say A sub I sub 1, A sub I sub 2, out to A sub I sub m. You define them similarly. Okay, so this would be the number of objects having all of these m properties, right? Let n naught equal the number of objects having none of the properties. So in our previous example with the beads, the question we asked was how many beads weren't glass, weren't red, and weren't spherical. That would be our n naught here, right? Okay. So now we can state the theorem. This is principle of inclusion and exclusion. Okay, using this notation above, this just says that the number of objects having none of the properties is the total number of objects, right? Remember, I said my answer is the total number of beads minus everything in this set. This is now giving a way to compute this explicitly. This is the total number of objects minus the sum over I of the numbers of objects having individually the single properties plus the sum over I less than j of numbers of objects having both a sub I and a sub j properties. Again, you might say, why is this sum I less than j? You've just done this labeling in such a way that this comes first, right? It doesn't matter what order these arrive in. The order, this is like ordering the sets in an intersection, right? It doesn't matter. A intersect B, B intersect A. Those are the same things, so this doesn't matter what order it is. This is just a convenient way of organizing these sums. Minus, remember these are alternating. All right, this is where the inclusion-exclusion terminology comes from. The sum over I less than j less than k of properties, number of objects having properties ai, aj, and ak, and plus continues on in this alternating fashion, plus the, like a completely generic term here is minus 1 to the m times the sum over indices I sub 1 less than I sub 2 and so on out to I sub m of the number of objects having the m properties. Actually, I didn't use commas here when I use this notation, so there. On out to the very last term, which is minus 1 to the r times n with all of those properties, a sub 1 out to a sub r. Okay. All right. So this is exactly, like, reading it off like this might be a little bit confusing. Don't try to think of it just in terms of the notation here. Think about it in what you're doing. So this is fundamentally the same as here, right? So here we're doing the final answer, so the signs are flipped. So you have minus, plus, minus, plus, so it's flipped around. Because, again, what we're doing is this total answer, which is total number minus this. So yeah, it flips the signs. But ultimately, the point is it's alternating, and it's alternating as here's the sum of the number of objects having the properties taken one at a time, and then alternating sign, sum of total numbers or numbers of objects having properties taken two at a time, alternating sign again, number of objects having, so it's the sum over the number of objects having properties taken three at a time. Again, alternating sign, so it's as you pass to the next step, you're taking more and more properties and you're alternating the sign, summing over each of these. How many are in each term? Well, how many are in each term can be computed using binomial coefficients, as we're going to see here. So I'm going to leave this theorem stated here. I'm going to put the proof beginning on the next page. So maybe I'll leave this theorem stated here and put the proof here. So proof. Okay, suppose an object satisfies none of the properties. Okay, then the expression on the right counts it precisely once. And where does it count it? It only counts it in this term. It's not going to be counted anywhere here because it has none of these properties, and by definition, this notation n of a sub I, n of a sub I, a sub j, and so on, these are numbers of objects having the indicated properties. So if it has none of these properties, it's not counted anywhere except in this first term. So then the expression on the right counts it exactly once in the n term. Okay. Now, on the other hand, suppose an object satisfies exactly m of the properties. Okay, so m is some positive number. M is greater than 0. Okay. Then when is this counted, right? When is such an object counted? So it could be counted, I mean, well, not could be, it definitely is counted in the n term here since every object is counted there. Okay. Where else is it counted? So if it contains exactly m of these properties, well, or if it satisfies exactly m of these properties, well, I need to know which properties it satisfies, but I can, by the structure here, I can actually say, okay, well, it's going to be counted m times here, right? Because if it satisfies m properties, then m of these a sub i's, right? You could label them a sub I sub 1, a sub I sub 2, out to a sub I sub m. It satisfies each of those properties, so it's going to be counted m times here. So then it is counted once in the n term, m times in the term that takes these properties one at a time. And there's, of course, sums here, so since we're summing over them, it's counted m times. M times in this term. How many times in the second term? So in this second sum term here, how many times is it counted? Well, I have m properties, and it's going to be counted if I have 2 of the properties from the m that are included here. So how many ways can I choose 2 properties from m properties? Well, m choose 2. So m m choose 2 times in the sum over properties taken 2 at a time. And in general, for the same reason, m choose k times in the kth sum term. So I mentioned in words when I was saying if you wanted to know how many terms you have to worry about in each case, you can figure this out with a binomial coefficient. This is exactly what we're doing now. Thus, the total contribution on the right-hand side from such an object, here such an object is referring to an object satisfies exactly m of the properties, right? Thus, the total contribution on the right-hand side from such an object is, I'm summing these binomial coefficient terms, but they're alternating. So this total contribution is the sum over k, it's an alternating sum of the binomial coefficients m choose k. But we know what an alternating sum of binomial coefficients are. This is just an alternating sum across a row of Pascal's triangle. We know that's 0. So an object satisfying exactly m of the properties where m is greater than 0 contributes 0 to the right-hand side. It is not a thing. So then what is being counted here? Exactly the number of objects that satisfy none of the properties, which is what our principle of inclusion-exclusion says. Okay. All right. So this is a very nice fact. This is, again, when you first see this, you say, well, okay, this might be true, but like this seems like a pretty narrow range of applications, because in your mind, maybe you're just thinking of that particular set example with the Venn diagrams. But actually, if you read through this thing, right, this is phrased in a way where indistinct objects satisfying some number of properties here, like this is actually vague enough to apply to a lot of situations where you might be worried about the count of a thing. And so, some applications. Of inclusion-exclusion. So what are some applications of this? So first, let's define what it means for two integers to be relatively prime. So two integers are relatively prime if their greatest common divisor is 1. Okay. So that is, say, m, n are relatively prime if and only if their GCD is 1. Maybe you're used to writing GCF here, greatest common factor, instead of divisor, doesn't matter, GCD, GCF, same thing. So, of course, this is a property that two integers can have in relation to each other. You're not just going to say 5 is relatively prime. That doesn't make any sense. You're talking about a pair of integers being relatively prime. So the Euler phi function, also known as the totient function, what does it count? If n is a positive integer, let phi of n denote the number of positive integers m less than or equal to n that are relatively prime to n. Okay. As you can imagine, this is important in number theory. Okay, for a variety of reasons, but as number theory is interested in studying numbers, say primes are the building blocks of integers, right? Talking about numbers being relatively prime is related, of course. In fact, you might already, even if you haven't seen this before, you might already be thinking about what the Euler phi function is when evaluated on a prime, right? And so it turns out we can actually write out a nice closed form expression for this using inclusion-exclusion. Okay, and so all I have to do, so what is the idea? Is to use inclusion-exclusion to compute a formula for this. But then I need a kind of a sub-idea here. If this is what I'm going to do, right? If my plan is to use inclusion-exclusion to compute a formula for this, like how would inclusion-inclusion help me here? I need to define a set and list of properties, or list a number of properties, such that the number of elements in the set satisfying none of the properties is exactly phi of n. Right? So I need to come up with a set and list a number of properties such that the number of elements in the set satisfying none of the properties is exactly phi of n. Then I can just read off the formula, hopefully, using inclusion-exclusion. And so, to do this, suppose our number n is divisible by exactly r distinct primes. Okay, which we label p sub 1 through p sub r. Select the set of the first n natural numbers as your set, let A sub I be the property is divisible by P sub I. Then the number of elements in the set that satisfy none of these properties, not divisible by P sub I for any I, is going to be the same number of integers relatively prime to n. Why though? So here is where, if you haven't had any number theory or you haven't thought, or algebra, you haven't thought about this that much, you're gonna have to think a little bit. So let's do the negation here. So let's think of what would happen if this wasn't the case. So for instance, let's suppose that a number is divisible by some P sub I. If it's divisible by P sub I, we know that such a P sub I also divides n. So then n and this other number I'm thinking of would have exactly at least P sub I as a common factor. So their GCD would be at least P sub I, whatever P sub I is. Remember, 1 is not a prime, right? So so this is going to be at least 2, so it's going to be greater than 1, so it's not going to be relatively prime. So the only way such a number is relatively prime is if it's not divisible by any of these P sub i's, because being divisible by a single one means it has a common factor greater than 1 within, so it wouldn't be relatively prime to it. So then exactly the things that are not divisible by any of these primes that divide n, that is exactly the numbers relatively prime to n. Okay? So again, if you need to pause and replay that explanation, go for it. But this is what's being enumerated here. Okay. So what about the right-hand side terms here? So for instance, now for the right-hand side, and when I'm talking about the right-hand side here, I'm talking about the right-hand side for this principle of inclusion-exclusion. So what do I do? So here I'm looking like I'm going to go one by one, in, and then the terms involving a single property, then the sum of the terms involving 2 properties and 3, and so on. I'm just going to go one at a time here. So in this case is the total number of objects in. Okay. Of course, n of a sub I is just little n divided by P sub I. Again, think about what this is. So this would be the number of objects satisfying exactly a sub I. Property a sub I is divisible by P sub I. How many of those are there? Well, n divided by P sub I. Right. What about this? Again, think about why this is. And so on. It's going to be like this in every single way. And so, using inclusion-exclusion, the number of objects with none of the properties, that was phi of n, the Euler phi function, and this is equal to n minus the sum over I of, n over p sub I plus the sum over I less than j of n over p sub I p sub j minus the sum over I less than j less than k of n over p sub I times p sub j times p sub k, and so on out to the very last term, which is minus 1 to the r. I said minus 1 to the n, I meant minus 1 to the r. It's minus 1 to the r times the single term n over the product of all of those primes. Okay. But, like, every single one of these has an n in common. And the pattern here of how these can be factored is the following. This is n times the product, I equals 1 to r, of 1 minus 1 over p sub I. So if you're a little bit confused about this algebra, just start with this product, expand it, and see how it is equal to this expression. Okay? But with a little bit of algebra, this simplifies. You see how the n pulls out, so you're left with ones in all these numerators, and then work out the algebra here to see that we have exactly this. So this is an exercise. This is going to be maybe not in your next homework, but maybe on a future, who knows, maybe a future exam or something. But this going from here to here is something you can do on your own. Again, I suggest starting here, work backwards. You'll see how this goes. Okay, even if you're just doing it in a brute force way. Okay. Notice you might not believe this all of a sudden. Like you might say, I don't know. Like I don't know what to say here about this. Let's try specific examples. Okay. So the primes dividing 24 are 2 and 3. Right? So phi of 24, according to this formula, would be 24 times 1 minus 1 half times 1 minus 1/3, which is 8. So supposedly there should be 8 integers relatively prime to 24, 8 positive integers. Note 1, 5, 7, 11, 13, 17, 19, and 23 are relatively prime to 24, and there's 1, 2, 3, 4, 5, 6, 7, 8 of those. All right. Okay, you can check this with a few others. So this is saying that a form for this Euler-Phi function is exactly this product involving the primes that divide it. Okay, the primes that divide n. So you can imagine, like, how would you have approached this count without inclusion-exclusion? It's kind of hard to think about what you would have done to sort of fix this, right? But nevertheless, this is this is a tool in our toolbox now, so we don't have to worry. Whenever we can try to bring it to bear in a similar way, it's something. It's an option. It's on the table for us. So I'm going to next time. Next time we are going to do a couple more, so a few more applications of inclusion-exclusion. Then on to generating functions. So I think here is a good stopping point before I mention, as I said, a couple more applications of inclusion-exclusion before we get to another big tool in our arsenal, which will be generating functions. And then it will kind of, our study of this topic will kind of branch out from there. But anyway, that's all I think for today. I think the previous lecture was like 10 minutes longer than it should have been, so this lecture is like 10 minutes shorter than normal. So between those two lectures, it is evened out to be an hour and 20 minutes each. So I think now's a good time to stop. So I will see you all on Monday.